Can I do what? Scooch up right now. I'm going to leave it up as is just so everybody can kind of get to it. You can stand up, scooch up, whatever. I can zoom in here in a second too. It's h of. Yeah, like h is like a function, like f of x, g of x, h of 2x. One of the, as I walk around and talk to you guys, this is the questions and such. One of the more common themes is like, what in the heck is h? Right? Maybe some of you have that same thought. H, I would just say h is a name of a function, just like some functions. Some functions are named f of x. This one is named h of x, and it just so happens that the input is 2x. So the h of 2x, which creates some chain rule stuff, which make you think a little bit more, I suppose. But the derivative of h is just h prime. Right.
How did you get to h prime?
How did I get that? So it might have been better written as this. I'll write out the whole thing for you. So if I'm going to do d dx of h of 2x, I need to recognize that that's composite, and the big outside box is h, and the tiny box is, I'll start over. I need to recognize that it's composite, and the big box is h, and the little tiny box on the inside is 2x. So I need to do a chain rule.
Oh.
So the derivative of h of something is h prime of that something, but then I do have to multiply by the derivative, and I think you just saw it of the inside, so times 2. I just put the 2 in the front because I saw that it was going to be a chain rule anyways, and that just felt like more of a normal way to write it. But if you wrote it that way, that'd be fine too. Yeah. What else? Dig deep here, ask questions. Even if you got them all right, maybe you felt lucky on one. You're like, oh, I'm not really sure why that is, or I don't know, whatever. So a good opportunity to discuss. Yeah, Shay, what's up?
So on question 3,
Yep.
can you just walk us through the first equation? It's so you do low, which is the h of 2x. And
Yeah.
then d high, so
Let me
derivative of
I'll use a highlighter here. So
derivative of something to the x would be
So, yeah.
of a.
ln of a times a to the u times the derivative of the inside. So I'll just do this off to the side. So d dx of a to the u would be ln of a times a to the u times u prime, with the u prime being your chain rule factor, I guess the derivative of that inside. So then when I see, I'll highlight it, I'll try to go color coordinated here. So here and here, does that part make sense?
Yes.
The reds?
Yeah.
And then I would say that the blue highlight and the blue highlight would be the same piece of the puzzle. And then the green highlights would go together as well.
Yep.
That make
So
sense?
that's the chain rule on
On the
the
numerator, 5 to the 4x.
Okay.
Yep. So that's your low D high minus and
High.
the yep. So there's your high in yellow, and then D low. That's what Brennan was just asking about, like the derivative of h of 2x. would be, this right here is the derivative of the big box. This right here
it's
is
just a function, you
the
don't
little
have-
box.
Okay.
Yeah, because we don't have a clue what h of x is, and it doesn't matter, because we know that the derivative of h is going to be h prime of whatever times the derivative of that same whatever.
Okay, yeah, I get it, except for
Okay.
So that's a change.
I just didn't know the A to the U thing.
So that would be a good one to go back.
Yeah.
So that was, in its non-chain rule form, that was included in our quiz 4.
Yeah, without the U.
Without the u, it just was an x. And so now with the u, that chain rule is in effect, we're going to be multiplying by the derivative of that u.
Okay.
I can tell by your
Anything else?
Nope, that's good, thank
Okay.
you.
Ty, what's up?
So, can I go on with this year's question? I don't really understand where that 2 came from before.
This 2 right here.
Yeah, I get that 8 I just want to get rid of
Okay.
it.
So it's the short answer to your question, Ty, chain rule. Would you agree that this right here is d low?
Yeah.
So d dx of h of 2x. So the key to this whole thing is recognizing that h of 2x is a composite. Does that make sense?
Oh, I got you now. You just said, yeah.
So would you agree that h is the big box?
Yeah.
So the derivative of h of something would be h prime of that same something. But then you saw where the 2 came from?
Yeah.
It's the derivative of the inside. So times 2. I just wrote it in a different order.
Why would it go? Okay, oh, no, okay, I got it.
Are you sure? Okay. What else? It's a lot of stuff in there, right? There's a lot of details. And I would say, like, this is complicated enough. If you're handling this okay, you're doing great. I mean, amazing, awesome. If you just ran through these 3 and didn't miss anything, that's incredible. If you ran through these 3 and you had some, listen, if you had some little details missing, you know what that means? It means you're in process. You have not arrived yet. That's okay. This is not a test. This is not the Unit 2 test. This is just a practice, and it's designed for you to learn from. So I'm trying to make these, honestly, some of these warm-ups, I'm trying to make like artificially hard to expose your strengths and weaknesses. Because it's just practice. So don't stress. Just get a little bit better. Shay.
On the first one, why did you put the 15x to the 4th minus the 4? Like on the end,
Yeah.
where did that come from?
So it's a product rule, right?
Okay.
Like I'm saying the whole thing is a product rule.
Yeah.
So this is 1. This is d2 plus 2. Oh, wait, no. Oh, sorry. I made it too big, didn't I? Oops. So how about 1 d2 plus 2. So this right here, I think it's important to recognize that whole thing is d1. It's the derivative of the first term. So what this is right here is d dx of e to the 3x squared, or 3x to the 5th, excuse me, minus 4x. So isn't the derivative of e to the something just e to the something
Yes.
times the derivative of that something? And that's where, because the chain rule, we fall victim in math, and I'm doing my best to bust you out of this. We fall victim to compartmentalization, like that was chapter 1, and now it's chapter 2, and the 2 shall never mix. The truth is, math is more like spaghetti than it is like waffles. Do you get the analogy? Waffles, you have all the little cubes, and you plop your syrup in each of the little cubes, and they got the little pastry walls that divide, right? Math is like spaghetti. It's all tangled up. But we want to compartmentalize it and say, well, we put syrup in this little thing, and now we're to this other little cube, and well, we can't break that wall down. I want to take my fork and just smash up your waffle and mix it all up and put it in the blender and turn it into this mishmash of syrup, butter, and waffly goodness. Right?
That would taste good, but I don't think it looks
It would look terrible, but it would taste good. Yes. So my point, Shay, with saying all that is the chain rule is always there. The chain rule is going to be that one spaghetti noodle that weaves its way through everything. At no point this year will I say, And we're finally done with the chain rule. I will never say that.
That's the big box, little box.
It'll always, yes, chain rule will always be there.
We'll never be done with the chain rule.
No, you'll never, not in this class, you'll never be done with it. It'll always be in the background, or it might be in the forefront. It'll always be there.
Okay, so it's the chain rule because the e to the x is being multiplied by a derivative.
It's more than just e to the x, though, right? It's e to the something,
Yes.
and the something is way more complicated than just an x. It's whatever it is.
15x.
3x to the fifth minus 4x.
Okay.
And
then
so,
I think we get that.
so we always multiply by the derivative of the inside. Check this out. This might help. This might help a lot of you. So there's where that comes from. Did you know, let me do this in a different color. Did you know, I mentioned this before, the chain rule has been there the whole time. If I did d dx of e to the x, wouldn't you say that that's just e to the x? But I would say, technically, aren't we multiplying by the derivative of the inside? Which is a 1. So it's always been there, and it always will be there. Sometimes it just shows up as an inconsequential times 1, and other times it's a lot more consequential, like on this one. So it's always there. Please don't ever think of the chain rule not being there, because it always is.
Yep.
It is. Anyway. All right. Anything else? Okay. Well, we got some work to do. Let's revisit what we did last time, and that is implicit differentiation, the weird
Can we
thing.
just call it the weird thing now?
No, it's not weird. It's very nice.
Right now it is because we don't get it very well.
You're not there yet.
Take the derivative of y, you just add dy dx.
No, you don't. It's a chain rule factor. You multiply by the derivative of the inside. I mean, honest to God, I'm not trying to oversimplify it. That's all it is. You're simply multiplying by the derivative of the inside.
What real world application?
Oh, this is such terrible timing. I'm sorry, your question is a good one, but the timing is terrible. I don't have time to just say, hey, Anna asked a question, so let's just push the calendar back by a whole day. Be patient. Let me just say this, though, Anna. Remember what this unit is called. This is called Derivative Skills 1 and Derivative Skills 2, right? So you are learning the skills. Guess what the next unit is? Applications of derivatives. So you're going to learn a lot more in the next unit about where would I use this. It said like the whole next unit, the whole next package.
Unit 3.
Yep, unit 3. Hey guys, this one right here. So notice it says, and this one is a very generic version. It just says find dy dx. Please notice that currently the y is not solved for. This one you actually could. We're going to practice our implicit differentiation because in a lot of these situations you can't. So if I am trying to find dy dx, what action do I need to take? If I'm trying to find dy dx. Okay. This is incredibly good evidence. Shh. This is really good evidence that on my part I made a good decision that we should spend 2 whole days on this because you don't even know what I'm talking about. Here we go.
I feel like we're going to learn.
If I am trying to find dy dx, I need to do d dx to everything. I need to do the derivative with respect to x to everything in there. Here's how I signify that. I put that in parentheses and I write d dx. What I'm trying to communicate in that situation is I'm going to do the derivative with respect to x, specifically x, of all the stuff that's in those parentheses in that equation. What do you guys see as far as procedures and such? Do you see anything jumping out at you as like, oh, we need to do this, so we need to do that? Bex, do you see anything? Oh, how many? 2. Do you guys see them? Here's a product rule right here. There's another one right there. She's right. So let's focus on this first one. And what you guys are going to do is you're going to ask me questions if I do something that doesn't make sense. Okay? You're not going to just sit there. You're going to say, well, wait a minute, and we'll talk about it. We'll get it figured out. It's been done 1,000,000 times. You're going to be able to do it too. So in my first product, I'm going to call the yellow factor my 1, and I'm going to call the green factor my 2. You guys okay with that? So let's see if we can talk this out. Remember, it's for the product rule, it's 1d2 plus 2d1. What do you guys think the 1 is? Shout it out. 3x. Good. Now, that one was fairly straightforward. D2 gets a little tougher. What do you think D2 would be? It's dy dx. That's correct. Now, this would be a great moment for you to say, whoa, wait a minute. I don't get that.
Oh, wait a minute, I don't get that.
It is, I very much prefer this, but yes, same thing. We can go with that. You guys are going to really want to use this notation when we start getting to Anna's thing about applications and all that. All of a sudden, whether it's dy dx or dy dt is going to make a huge difference. It's kind of hard to tell with y prime. With this, it's easy to tell. Okay? So you're asking questions, right? Anything I can do to help? We're not done yet, but on this part, at least, I want to make sure. Okay, read.
Why'd you do that?
Why did I do that? Okay, so let's come off to the side here. So all this stuff with implicit differentiation is based on the chain rule. So I'm going to kind of rehash some old ground, but I think it's really good ground to go back over. If I did d dx of x to the first, you might look at that and say, gosh, Mr. Anderson, that is not a chain rule. But I think that I could kind of look at it like a chain rule, couldn't I? Well, check this out. I would say that this equals, wouldn't the 1 come down in front, and I would get x to the 0? If I just did a regular old power rule, 1 comes down in front, 1 minus 1 is 0. And then with the chain rule, don't we always multiply by the derivative of what's inside? So what's d dx of x? It's dx dx, also known as 1. So if you look at all this, wouldn't you basically get 1 times 1 times 1? Which is exactly what you would expect to get, because you all know the derivative with respect to x of x is just 1. But what if we changed our variable a little bit? That makes a huge difference. If I was doing d dx of y to the first, just like we did on this one, wouldn't we follow largely the same procedure?
Yeah.
Let's think this through. Wouldn't the 1 come down in front, have y to the 0? I'm just doing a power rule. The derivative of something to the first is 1 times that something to the 0. But now, when I multiply by the chain rule factor of the derivative of the inside, I got to remember that I'm doing d dx of a y. And that makes a difference, doesn't it? So instead of a dx dx, what do I get? dy dx. And then when you think about how this would all total up, don't you essentially get 1 times dy dx? Dy dx. That make sense, Reed?
Yeah, it does.
That's the kind of the mechanics of what's happening behind the scenes. Okay.
If our variable was t, t dx?
Yep. Or any other variable we can think of that might be important. Okay. Ty?
Just out of curiosity, so when you're saying it, do you have to say, do you say dy over dx, or do you say dy dx?
Great question. The standard is to just say dy dx, knowing that what we really mean is dy over dx. If you say dy over dx, we're all going to understand what you meant. And it's obviously you're slightly more correct than we are if we say dy dx, but that's just kind of the standard way to say it. Yeah, for sure. Good question. Okay, 1d2, are we good? Reed, thanks for saying something. All right, so then we go plus 2d1. What's my 2? Y. And then how about d dx of 3x? Just times 3, right? So at this point, I've completed the product rule on my first term, 1d2 plus 2d1. Ty?
So, okay, because you took the derivative of the...
Yeah, in the second term, I didn't do d dx of a y, did I? I did d dx of an x, right?
Okay, wait.
Oh, no, okay, so I got you. So it's just the
Derivative of 3x.
The d dx of 3x, isn't it technically 3 times dx dx?
Yeah, but it's just one.
And dx dx is 1. So why would I write times 1? I don't think I would.
Oh, I see. Yeah.
I would just leave it as is. Okay, and then I'm going to put minus, and I'm going to say red is my 1, and purple is my 2. Come on, there we go. Okay, so let's go through the same thing. I'm going to put this in parentheses because I'm subtracting it, right? I need to make sure I subtract the whole thing, not just the first term. Okay, 1d2 plus 2d1. It's another product rule, as you all pointed out. Let's see if we do any better with this one. What do you think the 1 is? 5x squared. How about d2?
dy dx.
Isn't that just d dx of y? It's the same as the first term. I put that in there just for a little repetition. So yes, you do get dy dx right there. Plus 2d1 would be y times 10x, correct. Equals 8, right? Because it's derivative with respect to x of 8x. It's just 8 times 1 for your derivative, so I just say 8. So I'll give you a minute to reflect. Think if you have any questions on that part. Ty?
Just for implementation goes, do you need to continue to print like the d and the dx in the parentheses like when you wrote the first equation?
Do I need to continue the dy dx in parentheses?
Yeah, so like
You're like moving forward?
No, I was moving back for just a second. So like
Oh.
the notation on the first
Oh, you're asking like, do I need to have this stuff and this stuff and this thing?
down there. Yeah.
You mean like on the second step? No. Do you guys hear her question? Ty said, do I need to have the ddx and the parentheses down here? I'm hearing you right?
Yeah.
The answer is definitely no. Can anyone explain why we don't need that there anymore, Ben?
Because ddx means like to take the derivative of like the equation that's given. So if it was still there, it would mean to take it again.
So like if you're doing like second derivative.
Yeah, if you were going to do some kind of second derivative with respect to x, then yeah, we do it again. But having that still there, you're telling me
You need to take the derivative.
I'm going to do it again. And we're not.
Thank you.
Great question. Little things like that can make a huge difference. I agree. Okay, so then what remains here is some fairly advanced algebra, right? I would probably distribute that minus sign. So I'd get 3x dy dx plus 3y minus this minus that equals 8. So just a simple distributive property with that minus sign. Remember, we're trying to get the dy dx by itself. So any strategies, any ideas on what you would think would be best?
You subtract everything that doesn't have the dy dx attached to it onto the other side. And then you just
That was well said. Get everything that doesn't have a dy dx on the other side.
Yeah.
Love it. Perfect idea. So I'm going to say that would equal 8 plus 10xy minus 3y. That looks pretty good to me. And I usually do this in one step. Do you see how if you did do that, do you see how the two purple terms would be left over there? What do I need to do with the two purple terms? Factor out. There you go. So I would usually write it like this. Dy dx parentheses 3x minus 5x squared. I would just mentally factor that out real quick. I mean, you can show another couple of extra steps if you want. This is what I usually do. And what should be your final step? Division. There we go. So if we were to, I don't know, sort of try to clean this up a little bit, I'll come up here and say dy dx then equals 8 plus 10xy minus 3y over 3x minus 5x squared. This would allow us then to find the slope of a tangent line, the rate of change of the such and such, whatever application it might be. We would be able to plug in some numbers and then interpret whatever the result would mean, figure out that something's increasing or decreasing, whatever. Ty.
So then if you have the previous tangency for this one,
Yeah.
like if it was given to you originally, then you would just plug that in?
Yep, and we'll do that on the next one,
Oh.
if I remember correctly. Yeah, so if I told you, hey, let's find the slope of the tangent line at, I'm just going to make something up, it probably doesn't fit, 1,7. You'd plug a 1 in for all the x's, a 7 in for all the y's, and do some arithmetic and be done. Yeah.
And then is that how you want to get us to give our final answer, just like that?
Yeah, yeah, and the reason is, all it said is find dy dx. So at that point, you're saying dy dx equals all this stuff, and I'd say you're good. Okay, let's wrap it up. Let's flip over. Oh, Ben, question.
Should we always try to see if we can easily get y by itself on one side so that we can disregard?
Yes and no. Like, I think once you get the hang of this will actually be faster in a lot of ways. I would rarely, if ever, even think about that. I was trying to give you some easy ones to digest here, and frankly, the possibility of what you're talking about.
This one, it would be super easy.
It would. But I would say, to be honest with you, the likelihood of that showing up is very unlikely. So I would not get into the habit of I bet you I could just solve for y. I think you're going to be disappointed almost all the time. I maybe should change the examples. I wanted to kind of keep it simple for you, but maybe I should change that example just so that you're not thinking I could just do that. It's just not going to happen. Okay, so let's gosh, I want to resize this a little bit. Let's talk this through a little bit. This will be just about right. Hey, does the language in 2A look familiar to you? Yes. Have you not seen that over and over and over? And, I mean, right? Find the slope of a tangent line. Find the equation of a tangent line. You've heard this a lot. You'll continue to hear this. So like I said, with Ty's question, this one is really similar to what she was asking about because it says, at the point of tangency 1, 3, this is going to be right up your alley, what you were talking about, Ty. So what are the two things you got to have to find the equation of tangent line?
Point of tangency.
Point of tangency and?
Slope.
Of those two things, which one do you already have? Point of tangency, isn't it right there? 1, 3. What I need to do is find the slope of the tangent line, and this is where maybe implicit differentiation would be the right move. You might think this would be pretty easy to solve for y. If you did, wouldn't you get a plus or minus, a square root of something? And then you got to pick, do I want the plus or do I want the minus? And I would wager that by the time you're done thinking about that, I already have dy dx by using implicit differentiation. I think it would be faster here. Even though it might be sort of possible to do it without, I think it's going to be better. And in other situations, it won't even be possible to do it without. So it's worth practicing. So let me ask you, since we're trying to find the slope of the tangent line, symbolically, what am I talking about?
The derivative.
Specifically?
ddx.
Yeah, specifically I want dy dx, so I'm going to need to do d dx. So I'm looking for this to help me find my slope of the tangent line. So I'm going to come down here and I'm going to rewrite this. I'm going to write xy squared minus 8 equals x. And just like was suggested, I would encourage you to write this down. We need to do d dx to everything because we're looking for dy dx. That's our goal. Guys see any procedures that jump out at you like, oh, here we're going to need to do this or that? Ty, what do you see? Yeah, the very first term, right? It's product rule. Yeah. So this is going to be another chance for us to practice this. I'm going to call x my 1, and I'm going to call y2 or y squared my 2. So purple and orange on the colors there. So let's hear it. You guys all okay with 1 being just an x?
Yeah.
So here's x. Does anybody want to venture a guess on what d dx of y squared would be? Cole, what do you think?
2y dy dx.
What do y'all think of that? 2y dy dx. He is right on the money. He's exactly right. He's exactly right. Does anybody have a question about any of those parts? 1d2. Kenna? Okay. So, you're going to get tired of this answer. It's the chain rule, honestly. So, remember with the chain rule, like if I was going to do d dx of x in the box squared, wouldn't we say that this equals 2 times whatever's in the box to the first times the derivative of whatever's in the box? So, if I'm doing d dx of y squared, wouldn't we say, think about it like this, wouldn't we say that the derivative of something squared is just 2 times that something to the first? So I would say this is just 2 times whatever's in the box to the first. Turns out that in the box is a y. And then I'd multiply by d dx of that inside. There's my dy dx. Ken, I feel like somewhere in there you're like, oh, got it.
Yeah.
Did I read you right? Anybody have a follow-up? Okay, so there's 1d2 plus 2d1. So let's hear it. What do you guys think the 2 would be? Y squared. And then how about d1? d dx of x is just 1, so we're done with that part. What about d dx of minus 8?
0.
Believe it or not, people mess that up all the time. They just write minus 8. They don't think we're doing the derivative of all these things. And right, the derivative of a constant is 0. So you guys are right about that. And then this would equal what?
1.
Perfect. Okay. So far, so good? So then, let's see here. If I was going to try to solve this, doggone it, I didn't leave myself very much room. I'm going to come over here. If I was going to solve this, I would say dy dx equals 1 minus y squared over 2xy. Okay with that? We subtracted the y squared and then divided. Okay, so here's where there is another trap. Check this out. You might be tempted to do this. You okay with this part of my equation of the tangent line? You okay with that? So here's what some people will accidentally do. They will then take all of this and import this as the slope of the tangent line. Let me finish my point. And don't forget your question, Mitch. Why is that so wrong? Sorry, say again? Say again? It's not at a point.
There's Y's in there.
Yeah. So I would say, I think both of these suggestions are right. Number one, we want the slope at our point of tangency. And Cole says, well, basically that's not even a line. Right? Don't lines have constant slope? I mean, when was the last time a line looked like that? You've got y squareds and x's and y's multiplied together. I mean, that's not a line. So what I need to do is realize Kenneth's suggestion of I need to plug in 1, 3. That'll give me my actual slope of the tangent line. That's the number that I want. So maybe I come over here and say dy dx evaluated at 1, 3. And what is this? This is negative 8 over 6. So how about we just put negative 4/3 right there? Seem reasonable? A whole lot less scary looking? Yeah, because and here's why. What did it ask for? Is that the equation tangent line? We're good. We're good. So you bring up a good point because sometimes we see stuff and we just go. And we don't really pay any attention to what was asked. Like Ben brought up a really good point. Like on the warm-up, he went ahead and found the entire equation of the tangent line when it was only asking for slope. So sometimes we just do stuff and we don't even question, well, is this what we were looking for? So good question. Are we done? So I want to wrap this up by bringing up one last thing. We're going to kind of combine these last two into one little discussion. Do you see that green graph that's like partially there? It's kind of like off the screen a little bit. That is actually a graph of our original curve on Desmos. Kind of cool, right? Desmos will do all kinds of awesome stuff. Please check this out. I know we only have a few minutes left, but this is good. This will be hopefully good and useful for you. So would you all agree with me that if I did graph that line, it would look, I'm going to try to do this right the first time. It would look about like that. Do you see that red line I just sketched in there? Does that seem like a reasonable tangent line? Notice I picked the point 1, 3 for my point of tangency. I think I got pretty close. So that's what that would look like. So here is where I want to finish today. And you might question this, and I totally get why you would question this, but I would just ask you to kind of suspend your disbelief for a little bit. There are going to be times, and I think you can understand some of this for sure. There are going to be times when we want to use a line to approximate a curve. Can you think of why anyone would want to do that? Think really simple. Why would we want to use a line to approximate a curve? Say again?
It's hard.
What's hard?
The other way around.
Dealing with a curve
Yeah.
is harder than dealing with a line.
Yes.
Can you identify with that? He's right. That's a big reason why we would say, you know what? We got this pretty complicated looking curve thing here, and we're going to evaluate this or that. But if I said, you know what? Why don't we just use this really simple red line, and that'll be good enough for us? Wouldn't you be happy with that? Did you know that engineers are always happy with good enough, as long as good enough is precise enough? Like if you want your error to be like 1/1,000,000th of a millimeter, let's go there. Don't let perfect get in the way of good. Might as well be an engineer's mantra, right? And so sometimes a line is going to be an easier thing to handle, to Joey's point, than a curve. And that would be a prime reason to use a line, right? So when you see a question like B where it says use the tangent line from part A to approximate the curve at 1.2, somebody could bring up the point and say, well, don't we have the equation for the curve? Why would I bother to approximate? It's going to be easier to use the line. That's why. Does that make sense? So here's what you would do. It's not terribly complicated. We take our lovely equation from A, and we would just do this. Y minus 3 equals negative 4/3 times 1.2 minus 1. We would just plug the 1.2 in. Wouldn't this give us the y value for the line? Right? This would give us the y value for the line, and I'll just say that it's, 3 minus 4/3 of 0.2. And we can figure out what that works out arithmetically if we want. I'm going to say that this is approximately equal to the curve at 1.2. And wouldn't you agree that that's a whole lot easier to handle than trying to figure out what's going on with the curve, right? Just some pretty simple arithmetic. That's why we would do this, but that's still just like a little itty-bitty answer of why. We'll keep exploring in the future. So anyway, can you all see that the approximation would be too low? Can you see that from the graph? Isn't the line always below the curve there? So the approximation would be too low. I'm not too stressed about that right now. I just threw that in for just extra credit. So you guys are good to go. Have a good day. So Ty, what I'm doing, I'm going to zoom way in so you can see a little bit better. So
She said she could do that October date.
this line right here represents 1.
Uh-huh.
So wouldn't 1.2 be like right there?
Yeah.
In your Bible.
So do you see how when x is 1.2, like on this little imaginary 1.2 line? Thank you. Have a good day, Blake.
Oh,
Do you see how the line, the y value for the line is always a little bit lower than the y value for the curve?
y value of the line is always lower than the y value of the curve.
You see how the line is vertically lower than the curve? So if I'm going to use that line and say, well, hey, the y value of the line was slightly less than 3, I would want to know if the y value for the curve was going to be higher than that
Oh.
or lower than that. Can you see at least graphically, you see how the curve is always vertically above the line? So we'd say our approximation using the line was too low.
Is it always going to be like that?
Say again?
Is it almost always going to be like that? Except for unless it was like
Thank you,
flipping
guys.
instead if it was
So
like
thank
farther
you.
down. Like,
So it has to do with the concavity of the curve.
okay.
If the curve looks like this, the curve is what we call concave down, then wouldn't a tangent line always be a little bit too high?
Yeah, okay.
So and we'll explore that in the next unit quite a bit. I just wanted to throw this out there as sort of a, think about it.
Dude.
We'll get a little more detailed with it next unit. That's why. At this point, I would just expect you to look at the graph and say, hey, look, the line's always below the curve right there, so my approximation would be too low.
Oh, okay. Thank you, yeah.
Yeah,
that makes
for
more
sure.
sense.
Yes, ma'am.
I just wanted to make sure that I was a leader for presentation 5. I think I signed up for it, but I just want to make
Let's
sure.
see here. Yeah, you are for 5.
Okay, awesome.
Yeah, you are for sure for 5. Yeah, I was going to say something about that. The other class, person is going to be transferred out. So.
Yeah, and so should I submit that tonight or tomorrow?
ASAP, whatever you can. Mitch, what was your question about?
Thank you. I actually have
Oh, hi. How are you?
我挺好的，你好吗？
我也太好。
好就 OK。See ya。再见。Smart kid to Chinese. That's what happens. I am going to fit. Ooh, is that yours? No. Did she forget?
Yes. It was just there when I walked in.
I'm not sure what you're answering.
You guys can think of some really specific questions to ask
I'm gonna fail this quiz.
Me too.
What's the test on today?
Yeah.
Oh.
Yeah.
Oh.
Yeah.
Thank you very much. Appreciate your help.
Oh.
Yeah.
Sorry, excuse me again.
Yeah, so
Thank you.
I've